Deep beneath our cities, a silent engineering feat is taking place. While we go about our lives on the surface, massive mechanical giants are carving through solid rock and soft clay with surgical precision. These are tunnel boring machines, or TBM. They are not merely drills. They are mobile, self-contained factories that can exceed 100 meters in length and weigh over 5,000 tons. To understand their scale, imagine a machine as tall as a 5-story building, working in total darkness, miles from the nearest exit and under the weight of an entire mountain. The design of these behemoths traces back to an unlikely biological source, a wood-boring mollusk called the shipworm. In the early 19th century, engineer Mark Isambard Brunel observed how the shipworm used its hard shells to bore through timber while simultaneously lining the passage with a line-like secretion to prevent collapse. Brunel applied this tunneling shield concept to the first successful crossing beneath the River Thames. Today's TBMs operate on the same fundamental principle, protecting the excavation site while reinforcing the tunnel walls as they move forward. At the very front of a TBM is the cutter head, a rotating steel disc covered in specialized tools. For hard rock, the machine uses disc cutters made of tungsten carbide. These don't actually cut the rock in the traditional sense. Instead, they apply immense hydraulic pressure to the rock face, causing it to fracture and flake off in a process called spalling. The head rotates slowly, often only 1 to 3 times per minute, but with enough torque to pulverize granite. It is a slow, methodical battle of physics between steel and stone. The greatest challenge isn't rock, but soft, unstable soil. In these environments, the ground can behave like a liquid, threatening to collapse or sink the streets above. To prevent this, engineers use earth pressure balance machines. These TBMs maintain a precise internal pressure within the cutting chamber that matches the weight of the earth outside. By mixing the excavated soil with foam or polymers, the machine creates a thick paste that supports the tunnel face, ensuring the city above remains completely undisturbed even as a giant passes beneath it. Moving a 5,000-ton machine forward requires a unique form of propulsion. TBMs don't have wheels or tracks. Instead, they use massive hydraulic rams that push off against the very tunnel they have just built. Once the cutter head has advanced a specific distance, usually about 1.5 to 2 meters, the rams retract to make room for a new ring of concrete. This cyclical process allows the machine to inch forward, effectively using its own digestive tract as a stable foundation to exert millions of pounds of force. As the machine moves, it must immediately secure the raw earth. This is done by a vacuum-powered robotic arm called a segment erector. This arm picks up heavy, precast concrete segments and precisely fits them together to form a complete circular ring. Once the segments are bolted in place, a specialized grout is pumped into the small gap between the concrete and the rock. This creates a permanent, waterproof structure that can last for over a century, turning a raw excavation into a finished transit corridor in real time. The logistics of removing the excavated material, or muck, is an engineering feat of its own. A TBM can produce thousands of tons of debris every day. This material is fed through a screw conveyor or a slurry pipe and then onto a series of conveyor belts that can stretch back for miles to the tunnel entrance. In some projects, small narrow-gauge trains run constantly through the finished sections of the tunnel, bringing in fresh concrete segments and supplies while taking out the remnants of the mountain. Navigation in total darkness requires extreme precision. Even a deviation of a few centimeters can be disastrous for long-distance projects like the Gotthard-Base Tunnel, where 2 machines met in the middle after boring through 57 kilometers of the Alps. Modern TBMs use a sophisticated guidance system involving automated total stations and lasers. These systems provide the pilot with real-time data on the machine's position, pitch, and roll, allowing them to steer the massive cutter head with a level of accuracy that seems impossible for its size. Operating these machines isn't without risk. The tools on the cutter head eventually wear down and must be replaced. In high-pressure environments, this means divers or specialized technicians must enter a hyperbaric chamber at the front of the machine. They work in compressed air conditions, sometimes at pressures several times higher than at the surface, to manually unbolt and swap out the heavy steel cutters. It is a grueling, specialized task that highlights the human element behind these seemingly autonomous mechanical giants. Looking ahead, the engineering of TBMs is evolving toward full autonomy and extreme environments. Designers are exploring smaller, faster machines that could radically lower the cost of urban infrastructure. More ambitiously, researchers are investigating how TBM technology could be used to build pressurized habitats on Mars or the Moon. By tunneling deep into the lunar or Martian regolith, we could create colonies protected from solar radiation and micrometeorites using the same mechanical principles that allow us to cross beneath our rivers and mountains today.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.